Hi, all. Good morning. So, I'm so very glad to meet you all on a Saturday morning to be able to present about Kubernetes, especially about Kubernetes version 1.26. Um, this presentation is to give you a sneak view, a sneak peek into Kubernetes 1.26 version. There are actually totally 37 enhancements that are included in this Kubernetes version, but I would be actually presenting some prominent features and enhancements in this release. So let's get started. And by the way, if you have any questions during the presentation, please feel free to post them in the YouTube chat box, and I'll take some time to answer some of your questions. Okay, so here we go. Um, so let me give you a short introduction about myself. I work as a principal software engineer in Ericsson. So my role here in Ericsson is to design and develop cloud native MLOps platforms. So these are platforms that are responsible for handling the life cycle of machine learning models in a cloud native fashion. And of course, it is based on Kubernetes. I'm also the organizer of Kubernetes Community Days Chennai. We had our inaugural KCD Chennai event last year, and we are slowly gearing up to host the event this year as well. I'm the maintainer of an open source project called as QFledged. This is a project that is capable of caching container images directly on the worker nodes of Kubernetes. So if you want, you might want to take a look at the project itself. And regarding my interests, I am specifically interested in Kubernetes. I have totally 6 to 7 years of experience working in Kubernetes itself. In fact, I started with version 1.6 of Kubernetes, and also the wider cloud native ecosystem built around Kubernetes. And of course, MLOps, machine learning operations, which is all about how do you industrialize machine learning models? How do you actually streamline the process of managing the machine learning models as well as the applications? And finally, I'm also a keen learner, and I'm deeply interested in WebAssembly and what it holds for the future of computing itself. So I'm learning a lot on WebAssembly nowadays, and hopefully we'll be able to share some videos on WebAssembly down the lane. And you can connect with me on social media. I'm very active in Twitter and LinkedIn. And I also have a tech blogging site in Medium. And nowadays, it's a little bit passive, but hopefully in 2023, this year, I plan to publish many blogs. Yeah, the release itself, the theme of this release is called Electrifying. Kubernetes has started to give names, theme names to their releases, and this release is called as Electrifying. It also has a theme logo, which you can see it here. This includes a total of 37 enhancements. And by the way, the term enhancement in Kubernetes release parlance, it also means new features. Any addition to the Kubernetes project itself is managed via something called as Kubernetes enhancement proposals, and these are actually called as enhancements. So any enhancement can actually be implemented in three different stages. One is alpha, second is beta, and another is stable. So new features always are added as an alpha feature. So in this release, there are plenty of new features, but I'm going to pick out four new features and I'm going to talk about those four new features. One feature is actually graduating to beta, which is signing Kubernetes release artifacts. And the third one, which is actually entering the stable maturity, is CPU manager. And it is actually a very, very interesting feature which holds lots of promise for building, applications that require um, CPU affinity, which require complete allocation of CPUs in order to function. So I'll be talking about CPU manager as well. Okay, and again, if you have any questions, please feel free to post them in the YouTube chat. And whenever feasible, I'll take a pause on my presentation and I will take some time to answer your questions. So let's get moving. So the first feature that is actually new in Kubernetes 1.26 is validating admission policy. Um, so if you know about Kubernetes, whenever a new resource is created in Kubernetes, what happens is the request is actually submitted to the API server of Kubernetes, and API server itself has several admission controllers. So these are admission controllers which perform some validations on the resource content before admitting that resource and persisting that resource in etcd. Okay. Until version 1.26, the only method of doing validation on resources that gets created in a Kubernetes cluster is by way of using validating admission webhooks. So you need to basically create a resource called as validating webhook configuration. So this basically what it instructs is it instructs the API server to do a webhook post method to a separate application called as the webhook server, and the webhook server is actually responsible for doing the validation of the content of the resource. Now validating admission policy provides you an alternative method of doing the same thing but in a declarative fashion. So you no longer need to code your validating principles. So what is the validation policy? So you no longer need to code it, and also it provides an in-process alternative. So there is no more hopping of the request to a separate process or a separate container in the cluster, right? So it's fully declarative and fully in process, which is completely executed by the API server. Okay. And second thing is this uses something called as common expression language. So the common expression language is basically another open source project from Google, and the goal of this project itself is to come up with a common language, common declarative language, which multiple applications can use, multiple systems can use, so that these applications and systems can interoperate with each other seamlessly. And Kubernetes project has adopted common expression language in order to declare the validation rules of a validating admission policy. Okay. The specification of the language itself is so huge. I mean, that itself is a separate project. So we are not going to talk about CEL in this session, but I wanted to let you know that validating admission policy makes use of common expression language in order to define the validation rules. Okay. And by the way, how does this all works together, right? A simple validating admission policy is primarily made up of two resources. Okay. So the first one is the validating admission policy. The name of the resource is validating admission policy. This actually describes the validating logic that needs to be performed. And of course, this validating logic itself is defined by use of CEL, Common Expression Language. Okay. Basically, you need to actually know CEL in order to implement validating admission policy. Okay. And the next resource is validating admission policy binding. Okay. And this is the resource which basically binds the policy that you define in validating admission policy to the corresponding API resources onto which the policy has to be enforced. Okay. For instance, if you want to apply a validating admission policy on a pod, right? So you describe what fields have to be validated in validating admission policy, and then you create a validating admission policy binding in order to bind that policy to that particular pod, or you can even bind the policy to all the resources in a namespace simply by using namespace selectors. So these are different ways of binding the policy depending on what resources and what boundary onto which the policy has to be applied. So I have here are some couple of examples of how to use validation expressions using CEL. For instance, the first one actually performs some validations on min replicas, and max replica fields. So it says that min replicas should always be less than or equal to the object replicas, and the replicas should also be less than or equal to max replicas. So this is again CEL that you see. And of course, if you want to validate the that an entry with the available key exists, then you just say available in objects.stateCounts. There are various other CEL syntax available for you to actually build the exact validating policy rules that you want to build. But I'm not going to get more deeper into CEL or how to write CELs in order to implement validating admission policies. Okay. So the next feature that gets added to version 1.26, this is about pod scheduling readiness. So this is basically, let me give you a background on why this feature has been introduced. As you know, pods are currently considered ready for scheduling once created. So the moment you create a pod, either directly using kubectl, or if the pod is directly created by the control plane of Kubernetes, like a deployment controller or the daemon set controller, right? So what happens is the scheduler immediately picks up the pod and it starts finding a node for that pod the moment it sees the pod, right? Let's assume scheduler is not able to find a node that is fitting the pod. Okay, perhaps because some resources that are required by the pod are still not available. So what happens is the pod will end up in a pending state, right? And as long as the pod remains in pending state, the scheduler will keep running in loops in order to find a node for that pod. So what happens is this actually increases the load on the scheduler, and basically this is unnecessary overload on the scheduler, because apparently if the resource is not freed, apparently if the resource is not allocated, then naturally keep on retrying the loop within the scheduler is not going to benefit. So this new feature called as pod scheduling readiness, it provides a knob to flag whether the pod is ready for scheduling or not. Okay. This is called as scheduling gates within the pod specification. So what you do is whenever you create a pod, what you do is you add something called as scheduling gates, and you add a list of key value pairs in the scheduling gates section, right? So as long as the scheduling gate section has some entry, so in this case it has two entries, right? So as long as it has entries, scheduler will not pick up this pod. So it means the pod is not ready for scheduling, right? So only when external users or controllers, right, remove the list of key value pairs present in this section, only then the scheduler will pick up this pod and do the scheduling. By the way, if you are familiar with finalizers, right? Whenever you delete a particular Kubernetes resource, and if there are finalizers attached to that resource, what happens is the resource is not immediately deleted, right? As long as the finalizer has a content, the resource is not deleted. And only when an user or a controller goes and removes those finalizers, only then the actual resource gets deleted, right? So this is something very similar to that. So as long as the scheduling gates field has some valid list of key value pairs, the pod is not considered for scheduling. So the complete list of the key value pairs in the scheduling gates have to be removed in order to start the scheduling process itself. Okay, right. Let's move on. So the third feature I wanted to highlight in this presentation is called as feature metrics. Again, in order to understand what feature metrics are all about, whenever a new feature gets introduced into Kubernetes, what happens is it is basically introduced as an alpha feature, right? And Kubernetes gives you the facility of selectively switching on or off a particular feature. So not necessarily only alpha features, whether it is an alpha feature or a beta feature or for that matter even a stable feature, Kubernetes has this very good practice of exposing all these features as flags, and you as a cluster administrator, or perhaps you as an user of the cluster can determine, can actually decide what are the features that this cluster is going to support. Okay. This is actually existing for a very long time. It's not new. So it's called as feature gates. So in Kubernetes, this is called as feature gates. So this helps you to selectively turn on and off the features. Okay. Now let's assume you are a developer, right? And you are a developer and you are developing an application. And there is a cluster administrator who is responsible for this cluster, and the cluster administrator has decided that only certain features should be enabled on that cluster. But you as a developer wanted to know whether a certain feature is enabled or not, right? So that your application can actually perform certain logic depending on whether a feature is enabled or not, right? So until now, there is no way for the developer to dynamically know this, or for an application to dynamically know what are the features that are available on that Kubernetes cluster, unless you as a developer contact the cluster administrator and get this list, right? So feature metrics is a cool feature that helps you by actually querying the metrics endpoint of a particular Kubernetes control plane component and determine what are the features available, or what are the features that are enabled for that particular component. And this is very useful whenever you are actually more interested in developing applications that can be seamlessly ported across various Kubernetes distributions. For instance, if you are developing an application for GKE, so GKE, for instance, might not have enabled all the features, right? Perhaps there are some cloud providers which might enable a certain feature, and some Some might not even enable a certain feature, okay, depending upon the life cycle of how they want to roll out changes to the cluster. But if an application wants to know whether a feature is enabled or not, the feature metrics is a very, very cool method and a very useful method to find that. Okay. Okay, there is a question from Abhinaya. So Abhinaya wants to know, does this mean it avoid unnecessary pod restarts due to dependency? Okay, I assume this question is related to the previous feature on pod readiness. Okay, so pod restarts are something that happen once the pod has been successfully scheduled, right? So the pod restart is something that happens once the pod has been successfully scheduled and once kubelet on that particular node actually spins up the pod with the help of the container runtime interface. Okay, and once this pod has been spun up, and obviously, as you stated, the pod can restart because it is expecting some dependency to be fulfilled, or it is expecting some config map or a secret to be mounted. And if such dependencies are not fulfilled, naturally the pod gets restarted, right? You see it as crash loop back off in the state of the pod, right? And this happens after the pod has been successfully scheduled, whereas pod scheduling readiness is something like a knob that you can use to control whether the pod is ready for scheduling or not. So which means the pod scheduling readiness cannot actually cannot actually avoid these unnecessary pod restarts. So pod readiness comes somewhere even before the pod gets created, okay, but the pod restart happens because the pod has already been created. Okay, so that's the difference. Thank you, Abhinaya, for your question. Right, so feature metrics is completed. Let me move on. Yeah, the fourth feature that I wanted to talk about is dynamic resource allocation. And this is a very, very promising feature, I should say, because you see Kubernetes nowadays is deployed in different types of environments, and Kubernetes is also being used for running different kinds of applications. Okay, so there are, on one side, you have Kubernetes being deployed to various environments like Edge, right? So Edge itself possesses a unique set of challenges and unique set of resource needs, right? And there are applications, again, for instance, like machine learning applications, right? These are applications which has need for special resources. For instance, GPU. So the GPU is a very common resource that you come across in machine learning environments, or in fact, FPGA is another type of hardware resource that might also be required for certain telco grade applications, right? So increasingly, we are seeing that special hardware and resources based on the special hardware are being consumed by application. So dynamic resource allocation is an right step in actually making these generic resources available for pods. Okay. Before I get into dynamic resource allocation, there is a question from Sai. So Sai is asking, is this feature metrics kind of a governance done by the admins in Kubernetes cluster to restrict the usage of alpha and beta IAPA version? Yeah, that's an excellent question. It is certainly a mechanism to do governance. For instance, if your organization has some stipulations on how the Kubernetes cluster has to be configured, right? And if for security reasons or for some legal reasons, certain features should always be switched off, right? Then feature metrics is a very, very useful mechanism for performing these centralized governance checks. Okay, so you can simply write an application which periodically queries the metrics endpoint of all the components in across various clusters, and this can actually help in governance as well, of course. Yeah. And some and of course it is also, from a security standpoint, it is also a nice mechanism. For instance, if there is a security breach in one of your clusters and the intruder has activated a certain alpha feature because the intruder perhaps wants to perform some malicious actions on the Kubernetes cluster, and perhaps wants to exploit a vulnerability in a certain alpha feature or a beta feature, right? So when you actually have these feature metrics, and when you constantly keep checking on these feature metrics adherence by the Kubernetes cluster, you can also even catch these security breaches. Okay. So of course, yeah. So it is a tool for the developers as well who wants to develop applications that are aware of the features in the cluster, and of course, like you said, Sai, it could also help in governance. Okay, thank you for your question. Yes. So let's continue with dynamic resource allocation. So this API, the dynamic resource allocation, it actually has several APIs introduced under a new API group called as resource.kites.io. Okay. Basically, as I said, it is for handling generic resources. It is basically a generalization of the persistent volumes API. So if you are familiar about the persistent volumes API, like storage class, persistent volume claims. These APIs are existing in Kubernetes for a very long time for managing stateful applications, for allocating volumes of various different kinds, right? If you're familiar with persistent volumes and these different APIs, then it is actually very easy for you to understand the APIs of dynamic resource allocation as well, because basically what the project team has done is they have taken the persistent volumes API and they have sort of generalized it for different kinds of resources. The persistent volumes API are only for storage resources, whereas this dynamic resource allocation APIs are for any resources, any generalized resources. Okay. And basically, there is a role of third-party resource drivers. And again, this is very similar to CSI drivers, right? In the storage world in Kubernetes, there is a need for CSI drivers, okay? Container storage interface drivers, and these are drivers that are actually developed by third party storage vendors, right? And very similar to that, third party resource drivers need to be available, need to be installed in the Kubernetes cluster for you to define and manage these generalized resources. Okay. And again, these are the different API resources that have been created. So one is the resource class. This actually defines which resource driver handles a certain kind of resource. Okay. Um, the next one is resource claim, and with the resource claim is very similar to persistent volume claim. Okay, and resource claim can be either created by the user directly. So if the user wants a certain application to make use of a certain resource, right, then the user directly creates a resource claim. Okay, or very similar to persistent volume claims, the resource claim can also be created by the Kubernetes control plane. So let's say the pod specification itself has defined the resource claims. Then what happens is the control plane actually extracts that information and creates a resource claim for you. Okay. So basically, resource claim is basically a request to the resource driver to allocate resource instances. Okay. Again, very similar to PVC in the storage space. The third one is resource claim template. Resource claim template is basically you define a template for your resource claim so that pods can use the template, right? It defines the spec and some metadata for creating the resource claims. And again, this is very similar to persistent volume claim templates that you see within pods. Okay. Um, so basically, you have these three APIs which are exposed to the users. Then there is also a fourth API called as pod scheduling. This is actually an internal API used by the control plane, which is especially by the scheduler as well as the resource driver itself in order to coordinate the negotiation between the scheduler and the resource driver itself. Okay, because the scheduler, because you see, we are now talking about resources that are not managed by kubelet. Okay, in the case of CPU or memory or ephemeral storage for that matter. So these are resources that are completely managed by kubelet. So kubelet is very well aware of what is the amount of these resources, CPU, memory, ephemeral storage available in the node, and it will actually inform the control plane, especially to the scheduler, what is the available resources. But whereas these generic resources are completely outside the scope of kubelet. These are completely managed by the resource drivers. So you need a mechanism for the scheduler to understand whether a particular node will be able to fulfill the resource needs. Okay, and that can happen only by coordinating with the resource driver. So the pod scheduling API is especially for doing this coordination, and it is not actually exposed to the users. It is entirely used by the control plane for this coordination activities. Yes, there is a question from Sujit. Hey, Sujit, thanks for joining this stream. So, Sujit wants to know, do you think the incremental features in Kubernetes is causing increase in memory and space footprint of K8s to the point that this is becoming too huge and increasing latency? Yeah, again, it's a very good, thoughtful question. In fact, what I feel is this this is to a certain extent true, right? The reason is Kubernetes. If you see the roadmap of Kubernetes, or even the evolutionary path that Kubernetes is taking, right? It is more of consolidation and making it more robust and making it bulletproof robustness, and actually making it more pluggable, and making it more interoperable, making it suitable for running in various environments like edge. And there is also more focus towards making Kubernetes suitable for specific workloads, so a lot of thinking and feature addition goes into this space, and obviously, this will cause an increase in the footprint of the Kubernetes itself. So this is basically unavoidable, and you see, that's why to actually alleviate this process to a certain extent, the feature gates are provided. Okay, the feature gates will help you to actually turn on and off certain features. So if you feel that certain features are not going to be useful, if you see, by default, a Kubernetes installation switches on all the beta features, and by default alpha features are switched off, right? But if you feel that some of the beta features, or most of the beta features that are actually activated by default, are not required, so that can be switched off. um, so that is one lever that Kubernetes is offering in order to manage this increase in memory and space footprint over various releases. Yeah, I mean, that is where it is, Sujit. So naturally, more features are added to Kubernetes, and naturally, this will increase the memory and space footprint. And that's why you have these different distributions, specialized distributions out there, like K3s, K0s, and all these other distributions. Um, and microcaters also, which are trying to actually deliver a leaner Kubernetes version, which is much suitable for certain environments. But Kubernetes itself is actually the upstream Kubernetes project, I'm saying, is actually more focused on making Kubernetes more robust and making it, more pluggable and suitable for generally suitable for various environments. And of course, it's kind of inevitable that it will cause an increase in memory and other resource footprint. Thank you, Sujit. Thank you for your question. Right, so let's continue with dynamic resource allocation. Let me do a time check. Yeah, so we have 25 minutes more. Okay, so I'm going to just give you a brief idea on how dynamic resource allocation itself works in this 1.26 release. I'm going to do this by way of an example. The first thing is the resource class. The resource class resource is actually created by the cluster administrator. And the cluster administrator is also responsible for installing the particular resource driver onto the Kubernetes cluster. So the resource class is a must in order for pods to consume resources from the resource driver. So this is the first step. The second step is, as an user, right, you need to define what are the claim parameters. I mean, here, what happens is the resource driver, the vendor or the third party who develops the resource driver will actually make use of Kubernetes CRDs, okay, for users to declaratively specify the parameters. So every resource, right, will expose a certain kind of parameters, and users can actually customize these parameters so that they have a specialized and a specific initialized resource, and that is done by exposing resource specific CRDs which are developed by the resource driver vendor. And in this case, in this example, right, so the resource driver has exposed this claim parameters, okay. So as a user, I say that I need the color black, I need the size large. Okay. So this is something that the user of the workload has to specify. Okay. So this is like specifying that, okay, this is like the user saying, okay, I know this cluster supports this resource, but I need a specific configuration of that resource. Okay. And that is done by specifying or creating this claim parameters, right? So that is step number two. And step number three is where actually the user requests for a specific resource instance, right? So it's called as resource claim template. So what happens is within the spec, right, there is a resource class name field, which actually maps to the resource class that was actually created by the cluster administrator, right? So the resource class name should match a resource class that is present in the cluster. Okay. And the claim template can also specify parameters. Okay. By way of referencing the claim parameters that was created by the user in the previous step. So here you can see that the parameters ref is actually pointing to the claim parameters resource that was created in step two. Okay. So basically, a resource claim template is basically defining what resource class the resource claim is attached to, and also what is the exact configuration of that particular resource that is required. Okay, and again, this is created by the user when deploying in workload. And finally, this is where everything is tied together. If you see the pod manifest here, in the container section, uh, under resources, normally you will see requests, limits, and then specification of CPU and memory resources, right? So if you need to actually consume dynamic resources or generic resources, then you specify it in the claim section, and then you specify a name. Okay. Similarly, the second container also claims a generic resource called as cat-1. Okay. And there is a section called as resource claims. This is where actually the resource claims are defined. And how do I define the resource claim? Basically, by pointing to the resource claim template that was created in step number 3. And then I give a name to that, to this claim called as cat-0. And similarly, underneath, you can see a second resource claim being defined, which is cat-1, which is again created based on the resource claim template that was created in the previous step. So basically, this pod is consuming two resource claims. Okay. And what the first resource claim is consumed by the container 0. The second resource claim is consumed by container 1. Okay. So the moment this pod is created, what happens is uh, the scheduler will see that there is a request for a generic resource, and the scheduler will coordinate with the resource driver. The resource driver in turn allocates the resource and then marks this resource claim as allocated. And there are lots of things that happens between the scheduler and the resource driver. Okay. And eventually, finally, what happens is the pod will then be successfully scheduled only after the requested resources are allocated. Okay. To summarize, basically dynamic resource allocation is basically actually generic resource allocation, I would say. I don't think a dynamic resource allocation is a more appropriate terminology for this feature. Perhaps a dynamic generic resource allocation would be more appropriate. And this feature helps in requesting and allocating generic resources that are not managed by kubelet. Okay, so in a nutshell, that is what this feature is all about. This feature is all about requesting generic resources and allocating and consuming these generic resources that are not managed by kubelet and that are actually managed by a third party resource driver. Okay, and I foresee that this particular feature will be more useful in environments like edge computing and for workloads like machine learning down the lane when the edge computing or even in IoT spaces, right? So you have a plethora of hardwares, optimized hardwares and things like that. And I think this feature is a step in that direction to support all these various scenarios. Okay, good. So let's continue. I think we have some 20 minutes more. I think that should be enough time. Right. So I'm going to just talk about another important feature, which is signing Kubernetes release artifacts. Okay. And by the way, this is not a new feature in version 1.26. This feature was actually introduced in the previous version itself as an alpha feature. Okay. Basically, this feature is all about making the Kubernetes release artifacts verifiable. Okay, making these artifacts more trustworthy, right? And basically, signing is a process that is signing as a technology or signing as a tool is widely used everywhere. Okay, for verifying the integrity of any artifact. Okay, so it is called as digital signature. So you would have come across digital signatures being used, for instance, a PDF file, right? You might receive a PDF file that is digitally signed. So when you see a digitally signed PDF file, you can be very sure that the file originated from the person who signed that file. Okay, so you are very sure that this particular document is authentic and it is not tampered. Okay, the same thing is applied for the Kubernetes release artifacts. Okay, so the signing mechanism will make sure that the release artifacts are that the release artifacts that you download are completely trustable and they are not tampered in any way. Okay, So that is the whole idea and the whole advantage of signing Kubernetes release artifacts. This can prevent something called as man in the middle attacks. Okay. So what happens in this attack is a person will actually intrude into the traffic that is sent by the server to the client, and then the intruder will actually modify the traffic. Okay, so that the end user that is receiving the artifact will not be actually receiving the original artifact, but perhaps a malicious artifact. Okay, but signing will actually help you to get rid of these attacks. Okay, and Kubernetes itself has zeroed in on cosign as the tool for signing artifacts. So cosign is a tool that is developed as part of the Six Store project. You can look up the Six Store project in GitHub. This is again a Linux Foundation project, and cosign is a tool that is used by Kubernetes release team in order to sign the various release artifact. And again, um, another interesting thing of this feature is that it is actually signed in a keyless manner. Okay, all release artifacts are signed keyless using cosign, which means the end user, when they want to verify that artifact, they don't need a separate key in order to verify that artifact. Okay, this might sound a little bit crazy to see how an end user will be able to verify an artifact that has been signed without key. But I will actually probably encourage you to take a look at the cosign project itself. There is very good documentation on how on what keyless signing means and how it is done in cosign. Okay. um, in the alpha release of this feature, only the container images were signed like this. But whereas now in version 1.26, this feature has graduated to beta, which means not only the container images, but also all the rest of the binary artifacts, source code, tarballs, documentation, and the SBOM, the software bill of materials. All these artifacts are fully signed by cosign. Okay, so that's the difference between version 1.25 and version 1.26. All right. Good. So CPU manager is probably one of my favorite features. This feature is graduating to stable in version 1.26. Okay. Um, in order to give you an understanding of what CPU manager is all about, so let me take a back step and then discuss how CPUs are actually used by pods. Okay, let's say you create a pod, right? And the scheduler finds a node for that pod, and then the pod is actually marked as to be scheduled or to be started on that particular node. And then kubelet will actually be watching for pods that are actually marked for that node. And then what happens is kubelet will actually start the process of creating that pod. And as part of that process, kubelet will do something called as pod admission. Okay, so pod admission is the step in which the kubelet will perform some checks and really see whether the pod can be admitted into that node or not. So once kubelet determines the pod can be admitted, then it actually creates the pod sandbox, and then it coordinates with the CRI to allocate resources. In this case, let's say CPU resources, right? And then the CRI in turn calls the OS primitives. So because it is actually based on C group, right? The CPU containment is based on C group, and actually the OS itself will use some mechanisms in order to allocate CPU for the containers in that pod. And containers in Kubernetes can actually belong to three different quality of service. One is best effort, the second one is burstable, and the third one is guaranteed. Okay, so depending on these three quality of services, the CRI as well as the Linux kernel will determine how best to allocate and manage the CPUs. Okay, So what eventually will happen is the OS will allocate CPU cycles for the container. Okay, and the OS in some cases can also even um, migrate some CPU cycles from different from one CPU core to another CPU core. I mean, this is all part of the scheduling process of the OS itself, and it is a common practice, for CPUs to be allocated. So a container might be running on a certain CPU core, and it might even the OS might determine that it needs to be shifted to a certain different core, right? And this is all very transparent for the container. Okay, but this is all fine, right? So this is all fine, but there are some workloads which are cropping up, which needs very very strict um allocation of CPUs. Okay, what I mean by very strict allocation of CPUs is the way the OS handles or manages CPU allocation, the way the OS takes the liberty to shift the process among the various CPU cores might not be suitable for certain kind of workloads. Okay, and this is where CPU manager gives the ability to to actually define more specific controls on CPU affinity and exclusivity on the node. Okay, for instance, the CPU manager, right? It actually works on two different policies. The first one is a default policy, which means the CPU manager will not do anything extra. So it will just leave whatever CPU allocation process is existing as of today. But if the policy is set to static, it will allow pods to use increased CPU affinity and exclusivity on the node. So basically, what this means is I can actually deploy a workload onto Kubernetes, and I can say that this workload should have exclusive access to a certain CPU core. Okay, which means the OS cannot schedule any other process or any other container onto that CPU core, and that CPU core is dedicated for that container. Okay, so you can actually gain such a control over CPU allocation using CPU manager. Okay, the policy options that are existing for the static CPU manager are actually you can have three different policy options. The first one is full pCPUs only, which means it is a physical core, which means the container will be allocated a complete physical core. Okay. For instance, if you request a container um, with two CPUs, right? And if the CPU manager policy is set to static and the option is full pCPUs only, then two CPU cores are exclusively allocated for this container. And only this container can use that CPU core. No other process or containers can use that CPU core. Okay. The second one is distribute CPUs across NUMA. NUMA is basically hardware terminology. So instead of actually viewing the hardware as a monolithic board or a monolithic piece of hardware, NUMA will allow you to create some zones in the hardware, right? And you can have CPU cores distributed among these NUMA nodes, and you can actually decide to distribute CPUs across NUMA. Okay, so that is the second option. And the third option is align by socket. So align by socket is basically to prevent CPU allocation across NUMA. Okay, which means align by socket in the sense if the container requests two CPUs, the two CPU cores will be allocated within the same socket. Okay, so it means you get such a high degree of control over the CPU that the workload will enjoy. Okay, you can even say that you need you can say that this workload requires exclusive access to physical CPUs, which means cores, right? And you can also say that these two CPUs should actually allocated within the same socket. So within the same socket, for instance, if these two, if it is actually a workload that is actually doing lots of processing, okay, and this processing has to be done very quickly, right? So basically then align by socket is the container will have exclusive right over two CPUs, and the two allocated on the same socket, okay. So that is the kind of control that you get by using CPU manager. But your day-to-day workloads that you are currently seeing might not want to use the CPU manager to gain this high degree of control. But workloads like machine learning, workloads like streaming data processing, right? Or telco grade applications that are very very stringent on latency and performance requirements, right? Obviously will make use of CPU manager. Okay, I think I should do a time check. Yeah, there is 5 minutes more, and I'm end of this presentation. Um, so here have actually listed down certain resources which I have used in basically preparing this presentation, and all these resources are official Kubernetes documents. I actually encourage you to go through some of these documents. So if at all some of these features interest you, and if you want to learn more, please feel free to make use of these resources. I'll also leave links to these resources in the YouTube comment section so you can easily access these resources. Okay. Thank you all. Thank you so much for watching this presentation. And again, the release itself, it includes totally 37 enhancements, right? And today I was able to talk to you about six of those enhancements. So four of them are new features, one is entering beta, and the next is entering stable. And of course, there are much more features and enhancements that are listed down in the release blog. So you might want to take a look at that as well to see what are the other things that are get added in version 1.26. All right, I think we have reached the end of the show. Let me see if there are any comments, any questions. No. Okay. Fine, guys. Thank you. Thank you so much for tuning in to this live stream on a Saturday morning. Thank you so much for your wonderful questions, and hopefully, we will be able to meet soon in another live stream very soon. Thank you so much, and see you all. Bye.